Hi, my name is Saurabh, and I will be talking about a work on auxiliary tasks for point goal navigation. In point goal navigation, an agent is spawned in a never before seen environment and is expected to find its way to the specified point goal location, which is given in relative coordinates. In our case, the agents were either able to observe a RGB color or high resolution depth map view of the environment. They were provided goal location with a GPS compass. The map shown here is solely for the purpose of visualization and it is unavailable to the agents. The current state of the art for training point goal agents, DDPPO, is slow to train, taking millions or even billions of steps to reach optimal performance. We show that agents trained with our auxiliary task can achieve a significant speedup. Let us see the agent architecture. The PointNav agent consists of a series of convolutional layers to produce a visual embedding from observed input. This is further consumed by a GRU recurrent network to obtain a state representation which is used to get an estimate of the value as well as to derive policy. The agents may go forward, turn left or right or call stop to end an episode. The agent is trained via PPO algorithm. Let us see how we go about training a policy network in conjunction with auxiliary tasks. We choose a suitable intermediate component to be used by auxiliary network for the task. Thus, the agent is trained to learn a common representation that minimizes both the policy as well as auxiliary loss. It is important to know that the auxiliary network is not part of the agent architecture during inference. Let us see our three auxiliary tasks: quantized depth prediction, inverse dynamics, and remaining path length prediction. The motivation for quantized depth prediction comes from the observation that depth agents perform far superior to the RGB agents. This indicates that depth information is crucial for navigation. The auxiliary network used the spatial convolutional features from the RGB input to predict depth map. For our next auxiliary task, inverse dynamics, we train the network to capture the transition dynamics of the environment. For this, auxiliary network tries to configure the action taken by the agent to transition to the next position. For our final auxiliary task, that is remaining path length prediction, we try to teach the agents to make decisions taking longer range navigability into consideration. Specifically, we train the common representation to embed the knowledge of shortest geodesic distance to the goal by predicting it using an auxiliary network. We design auxiliary networks for each task that rely on different inputs from the base model. For more details, please see our paper. In order to build the indoor simulation environment for our experiments, we use Habitat Simulator with Gibson dataset. We build our agents on top of the existing code base and compare the results with the baselines. We report two metrics. A navigation episode is considered successful if the agent is within zero point 0.2 meters of the goal when it issues the stop action. We also report success weighted by the inverse path length or SPL, which weights success by the efficiency of the path, which is just a ratio of shortest possible path to the actual path taken by agent. Let us now see some results. We compare our task-equipped agents with the habitat baselines. As can be seen throughout the training, the performance of baseline agents is inferior to that of the auxiliary task-equipped agent, with task-equipped agents achieving higher scores within fewer training steps. Combining all the agents gives us the best agent. This is also suggests that there is some non-overlapping information contained in each of these tasks. Here we compare the baseline with two auxiliary tasks from previous works and contrast it with our best performing agent. Our auxiliary tasks seem to be more relevant than previous work for photorealistic environments. We analyze the behavioral effect of our auxiliary tasks on the agents. We find our agents collide less than the baseline throughout training with depth prediction leading to the largest reduction. Using a probe model, we find agents trained with remaining path length prediction produce internal representations that are more effective at decoding the agent's precise location. Finally, we find the remaining path length predictors act as openness detector, predicting high geodesic values when in dead-end rooms as shown in the above qualitative example. To conclude, auxiliary supervision is useful to improve the sample efficiency of point goal agents and embed crucial information about the environment in agent representation. For more details about our experiments and auxiliary task networks, please see a paper. Thank you.